There are two comparison tests, and we need them when we have series that look like the following. And we're going to go through these 4 examples today. And what you'll notice is all of these series look either close to being a geometric series or they look close to being a p-series. But due to some added addition, subtraction, or multiplication by annoying functions that are transcendental, in other words, logarithms and exponentials and trig and inverse trig, those are all transcendentals. So it's almost a p-series or almost a geometric series, but not quite. In order to compare them to series that we know how to determine converge diverge for already, we have to know what is required first to even be able to compare them to another series. Now, if you say the comparison test, you are referring to the top test that you see right there. Let me make my screen a little bit bigger. Usually, just to make sure that everyone's clear, we will say the direct comparison test versus the limit comparison test. But know that if you're using the limit comparison test, you have to use the word limit with it. Otherwise, it's referring to the direct comparison test. So, here's how they work. If you're using the direct comparison test, it's an issue of an inequality. So what I'm going to do is I'm going to draw that this is n, and on the y-axis, we are going to have the individual terms of the series. And I'm going to also write down that you're going to have your given series, and I'm going to refer to that formula as a sub n. What you choose to compare it to I'm going to call that b sub n, and your textbook does the same thing. So when I write the terms of the series, I'm referring to a sub n and b sub n. Now, let me first put on, we've got term 1, term 2, term 3, term 4, term 5 kind of thing. And there we go. What you are comparing it to, you know whether it converges or diverges. Most likely what you're comparing it to is at least having the terms head to 0. Because it's unlikely you would bother with this if that wasn't your situation. Now, let's say the series that you are given has its terms smaller. So if your terms are smaller than what you're comparing it to, and yet again, I forgot to tell you the initial necessity, and that is we're only dealing with positive terms. We have no subtraction involved, no negative terms. It's all positive terms. So we're above the x-axis completely at all times. So if I'm dealing with a series of positive constants and the terms that I have are smaller than the terms of a converging series, So if this inequality is in this direction, and what I compare it to is something that I know converges, would you say that that logically forces the given series that you're trying to determine converge? Boom. That's enough. If my terms are smaller than the terms in a series who, when added together, give me a finite answer, do my terms have to add to make a finite answer? Yes. And so that's the idea of the direct comparison test. But the inequality has to go the way you want it to go. And that's the fallacy of this. Or not the fallacy, but the Achilles heel. I would say that. So if what you're comparing it to is convergent and your terms are less than or equal to their terms. And I want to say that it's not necessarily for all n, but for all n starting at some n. It doesn't have to be, the inequality doesn't have to hold for the first few terms. So it's for all n as you head to infinity, not necessarily first few. Okay. But anyway, that's necessary to be able to say convergent. But divergent, you'll see the inequality is the other way around. And I want you to visually think about this aspect. The way that I should have left those. Let me put those back in. No. All right. There we go. If that wasn't true, if I was dealing with what I'm comparing it to diverges, is it helpful for me to know my terms are smaller than somebody who is infinitely large? Right. So the inequality has to work the right way. So you want your terms to be bigger than a diverge. And now I'll erase these. Because if you're adding up these y values of the red points, and you're getting infinity when you add them all up, then when you add something that's a little bit longer than that, you're definitely getting infinity. And that is the direct comparison test. The issue is, does the inequality go the direction you want it to go? Because if it doesn't go the way you want it to go, with the only thing that you can really compare it to, you're either out of luck or you need another test. Dun, 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 dun. And that's where the limit comparison test comes in. And I will tell you that I personally prefer the limit comparison test over the direct comparison test because I don't have to bother thinking through, is the inequality the way that I want it to be? But the thing is, each of these two tests has moments where they're not going to be able to help you and the other one can. So we need both of them. There are a lot of times where you could choose either or, and that's where you go with what you prefer. Yes, I will scroll back up. There you go. So what I'm going to do is I'm going to talk about what these tests are. I just talked about the comparison test. I'll go into the limit comparison test. And then I'm going to actually go through those 4 problems I briefly showed you and either show you that you can use both of these techniques and what's expected, or how one of the 2 techniques isn't going to work for you on top of that. So that's the comparison test. And I'm going to go, Oh my gosh, you took it away. There we go. That's funny. I like your background. Okay, anyway. So, limit comparison test. Let me explain this. Now, you're dealing with the series you're given and the series you choose to compare it to. And they have positive terms only. If you look at their ratio, the ratio of just the terms themselves, as you head to infinity, what is actually mattering? Because they don't explain in this what matters. They just say if you get an answer to the limit and it's positive, then both series converge or both series diverge. But let me explain what actually matters. What matters is you get an answer to this limit that is not zero and it's not infinity. That means that as you head toward infinity, your terms and the series you're comparing to's terms keep a ratio, a finite ratio between the two of them. If their ratio is heading to zero, they are not holding on to each other with a finite ratio. If the answer to this limit is infinity, they are not holding on to each other with a finite ratio. So for me, I picture these two terms having like a tether between them. And if you can show that they form a ratio that is a positive, real, finite number that holds them together by this tether, this finite tether. So if one of them is finite, the other one is just within a ratio finite as well. However, if one of them is infinity and you have this finite ratio tether, then the other one has to be infinity as well. That finite tether says we're either finite together or we're infinite together. But no one's heading off to infinity without the other one. And that's basically what that is. So before I wrote this down here so that I wouldn't forget to tell you these. So write these down or understand them. In your homework, these are inequalities you may need in your homework assignment that I'm not going to go over with my examples. Be aware that no matter what function you put into sine or cosine, the answers you get out of sine and cosine are stuck between -1 and 1. Period. I don't care what function you put into them. They are for sure stuck there. If you decide to square sine and cosine, that allows you to have positive numbers when you need positive numbered terms. But if you're squaring numbers between -1 and 1, now they are between 0 and 1, and they're forced positive. So be aware of these inequalities. You're going to need them for some homework problems. Additionally, inverse tangent, as long as you are dealing with, I will explain that in 1 second. With inverse tangent, as long as you are inputting 0 to infinity, if you remember the graph of arctangent, it's asymptoting up to pi over 2. And that allows you to write this inequality. Now, The premise of both of these tests, I'm going to erase a little bit, or maybe I shouldn't. Maybe I'll just do this. Ooh, I know. Change the color. What color? Maybe an orange. Okay. Positive terms. The premise is you are given a series who has only positive terms, and you compare it to a series that has only positive terms. If you have positive and negative terms, you can't throw it into a comparison test. So with that said, that's really the reason why they say that the limit needs to be this finite number that is greater than 0. Really what matters is that C is a finite number that is not 0. I want to have an actual ratio between these two. A ratio that keeps them together, to infinity together or to finite together. All right, now let's look at examples. For example 1, take a good look at it. And what is holding this back from being a P series? Yep. When I look at the denominator, I have my 2n squared, but then I'm adding lesser degree terms. And if I'm heading to infinity, adding 4n to 2n squared becomes obsolete. Adding 3 is laughable. But as far as if I'm heading to infinity, those terms are going to melt away. They're going to keep me from being able to be a P series. But the further I get to infinity, the more this becomes like what I want to compare it to. So the first thing you need to do is say your choice of comparison. And what would you choose to compare it to? I know what you meant to write. Yeah. Now, I know that some of you are going to want to just write 1 over n squared, which is fine. Just it may make your ability to show that this compares harder. If you want your life to be easier, okay, no scam, no. If you want your life to be easier, bring leading coefficients with it. The numerator is 5. If you want your life to be easier rather than harder, keep that. The leading coefficient of 2, keep it if you want your life to be easier. Now, a side note, you can take a constant multiple, pull it out of sigma, so that you can see the P series better. If I have a number that is finite or infinite, and I multiply it by 5 halves, it is still finite or it is still infinite. multiplying by a constant will not affect whether there is an answer to the series or not. So you are always allowed to pull a constant multiple out of your sigma and look at what's left and say, hey, that's a p-series. You don't have to write that, what I just wrote. But you want to, when you decide who you're comparing it to, usually right away you're thinking what it is and whether it converges or not. So this is a good time to write that down. So this is a p-series. The p is equal to 2. Now, it is ideal, but I will not push it. It is ideal for you to say that 2 is greater than 1, and that's why it's a converging p-series. Converging, converges, or converge, it doesn't matter what. Oh my gosh, I all of a sudden forgot the word tense, what tense you put it in. So understand that it's ideal for you to express the inequality that is causing the converge diverge. I'm not going to push it on the test. I've learned to kind of let that go a little bit. But if you want to make sure that you're ready for whatever anyone expects of you, write that. Okay. Now, the only thing left to do is to use one of the two comparison tests to say that your series is converging also. I prefer the limit comparison test, but I'm going to start with direct. If I use the direct comparison test, then I want to write down the series formula that I'm given. I want to write out what I chose to compare it to. And then I need to allow myself to figure out which inequality this is. And I will tell you something. Many times I've graded tests where people put an inequality that is true, but I seriously question whether they actually knew it was true and just used it and hoped it was. So I try to create things on tests where the inequality won't go your way, because I want you to check it. You should be checking to make sure that the inequality is the way you want it to. Now, this situation, the quickest way to work with this is to think about, if I add to the denominator only, I'm making the denominator bigger. If I make a denominator bigger, I make the entire fraction, fill in the blank, smaller. So that means that this is my inequality, and I need to make sure, I need to think about it and make sure that this is what I needed. My series is smaller than a known convergent series. Yes, that's what I wanted. I wanted to be smaller than a converge or bigger than a diverge. So at this point, you could say that the final answer to the initial question is converge. And if you have not already stated them within your work, make sure you know that the tests used were two tests: direct comparison and p-series. Anytime you use a comparison test, a second test must go with it. A comparison test on its own isn't sufficient. No, you're not going to be asked what it converges to. There's some other things coming that I'll bring up. In this case, would it be 2? I'd have to look at it. Let me tell you this. You're not concerned right now with what the answer is. You're concerned with whether the answer exists or doesn't exist. And that's what these tests are for. They're only determining whether an infinite series exists or if it doesn't work. And because you need to know if something works or not. But they're not finding the value if it does work. It's just determining that it does. Okay, so that's what it would be if you were doing direct comparison test. If you were doing the limit comparison test, this is what it would look like. Now, technically, it does not matter whether you put the ratio as given series over comparator series or flip it around, because we just are checking to see that we are getting a finite ratio that isn't 0, so it doesn't matter who is the numerator versus denominator. The official test says the series you were given, oops, move my mouse back over, I knocked it. The series you were given in the first, there we go, yay, it's working, given in the first place, divided by your choice of comparison. Now look at that carefully, and how quickly can you tell me the answer to that limit? Yep. The answer to this limit is 1. All you need to do is get a positive finite number. If you allow the coefficients to come with your comparison, the limit is going to be 1. Most of the time, it also makes the direct comparison test easier, but that's not always the case. But for limit comparison test, keeping those coefficients that go with the terms that are leading this to infinity allow you to create something that is actually in a 1-to-1 ratio. And then limits 1, you're good to go. I'm not going to make you write the following, but officially, because this is greater than 0 and it is finite, we know that we end up with converge, this time by limit comparison test and p-series. So you can decide which test you like better in this situation. Either one works fine. I'm now going to move over to example 3, and then I'll go back to example 2. With number 3, what would you choose to compare this to? And essentially, you're just kind of getting out of there addition, subtraction that will be irrelevant if you're heading to infinity. Or I should say become less and less relevant as you head to infinity. And that's an N if you can't read that. I need to try that a little bit better. All right. Now let's quickly look at, is this a converge or diverge, and what test are we using on this one? So what I want to remind you of, let me actually just side note. If you see 1 over n squared versus 1 over 2 to the n, let's make sure we're really clear about the difference on this. This looks like a polynomial. That's a p-series. This one looks like an exponential. This one is a geometric series. So if it looks polynomial, you're going for p-series. If it looks like an exponential function, you're going with geometric series. So what is the R for this geometric series? Mm-hmm, 1/2. Now, it is very valuable. However, I'm not going to push it. It's valuable for you to say that the absolute value of the R you found is less than 1. Because that is what the geometric series needs. You're showing, hey, I'm verifying that I meet the requirements of the geometric series, but I have chosen to not push that. But I think it is good form if you put it in, if you want to be a good mathematician. Maybe I shouldn't put the word good, because that's a, if you want to be more clear, not a good, but a more clear mathematician, there we go. Then it's not putting a negative connotation so much. Never mind. Just trying to rephrase things to remember to keep out that positive negative connotation where it doesn't belong. Anyway, so we have converge. I'm going to erase away the stuff that is not pertaining to this problem in specific terms. And now we have to decide if we're going to use the direct comparison or the limit comparison, and if we can use both of them. So let's start with direct comparison. If I use direct comparison, I'm going to write down the equation that I'm working with and who I decided I should compare it to. And I want to take the time to think, which way does the inequality go? If I make the denominator smaller, I make that fraction bigger. And then take a moment to ask yourself, is that the inequality I need? It's not. So this is showing you an example of, you can't always use the direct comparison test because the inequality doesn't always go in your favor, even when it's obvious that they compare. And let me come back over to the example we had before. Had this problem, instead of plus 4n plus 3, had it been minus 4n minus 3, I wouldn't have been able to use the direct comparison test because the inequality wouldn't work in my favor. But the limit comparison test is still just as useful whether I have addition or subtraction. Limit comparison test takes it. What this means is, if you're showing your work on a test, you would prefer to cross this out. It was completely irrelevant to getting to the answer. So make sure that you understand it was not part of what is required to come to our conclusion. So now limit comparison. With limit comparison, I have limit as n approaches infinity, and then I write down the formula I was given divided by the formula I chose to compare it to. And what is the answer to that limit? One. And the reason why that matters is because it is positive and finite. In the theorem that we were looking at, it just says greater than 0 and finite. This means they both converge or they both diverge, so I'm ready for my conclusion. My conclusion is the series I was given converges. And to clarify, the tests used to get there are limit comparison and geometric series. And if I didn't say it already, usually when you're doing a comparison test, it's with a p-series or a geometric series. All right, so that showed you an example of the limit comparison test sometimes is necessary because direct won't work. Now let's go over to example 2. And I just realized that I'm going to be better off if I move this, which is actually why I stacked them the way I did. I can easily move this to where I can do work separate from the other ones. Okay, now this one involves, we are bringing in a transcendental function. Transcendental function means I'm dealing with an exponential function or a logarithm or a trig or an inverse trig. Now, exponential creates the geometric series, so that's not a concern. But it's concerning when you get a logarithm or a trig or an inverse trig. And then the question is, how do you deal with that? You need to compare it away. But this one isn't obvious. Some of the ones you're going to run into will be obvious, some won't be obvious. When we went over the integral test, I mentioned to you that most of the time there is a way around it if you see it. This is one of those cases. Most people, given this problem, are going to throw this in the integral test. And I think you had this in your homework last night. And the integral test allows you to find out it diverges. But you might not think of doing this, but if you just kind of take the natural log out of the picture, you've got 1 over n. And tell me about this what direction would an inequality go between these two? And let me add on, provided that I'm putting into my logarithm a number larger than its own base. Because, at the beginning, there might be some issues. So, side note, as long as n is greater than the number e, and since we're only using integers, then as long as n is greater than or equal to the integer 3, then the natural log of a number 3 or larger will be itself larger than 1. Now, if I do use 1 over n to compare it to, is 1 over n a converge or a diverge? And I'm waiting. Is 1 over n there we go. It's a diverge. And if I'm using the comparison test, I need to be bigger than a diverge. I am, so I'm good. This works. I either want to be bigger than a diverge or smaller than a converge. So now what work do you need to put down? If you've already got the inequality written, hey, that's one of the things that needs to be done. Then you need to state that you are going to compare it to 1 over n. And you can say it diverges by there are actually a few different tests you can use. Might be easiest to just say it's a diverging harmonic series because they diverge. So you choose who to compare it to, number 1. Number 2, you figured out whether that comparer converged or diverged. Number 3, the inequality. That's all you need. You can now say diverge by the direct comparison test and harmonic. And I'm going to repeat, if you are using a comparison test, by itself it is not enough. It must have a second test involved to determine converge diverge. Now, I also want to point out to you that the limit comparison test in this case won't work. So I'm just going to throw that out there. So if I have limit as n approaches infinity of the formula I was given divided by my comparator, this is equal to the limit as n approaches infinity of natural log. And what do we happen to know is that answer? It's not finite. Because that ratio is not finite, I'm not able to use the limit comparison test. At least not if that's who I choose to compare it to, but not that you're going to find something else. But if I choose to use 1 over n, I cannot use limit comparison test. And I want to point out that when I say you can't use one of the tests, it's based on the choice of the comparer. There are situations out there where if you chose a different comparer, it would work. I'm not saying that there is one that you can find, or that it's easy to find, or that it's hard to find. Just based on what is chosen, whether that test will work or not for you. So in other words, this is a waste of time. And now that leaves us with one last example. And I am going to recommend to you to not use the direct comparison test in these situations. Granted, this one might be reasonable, but I'm going to throw out a general situation that's going to reoccur, and that is a situation where your formula is either a polynomial divided by a polynomial, and maybe there are roots involved. Maybe there are several roots involved. It could get worse, but I'm going to leave it there. If you essentially see something that is polynomial with maybe some roots as well, I recommend that you go straight to limit comparison test. You don't have to bother with the issues of, do I have pluses or minuses giving me the inequality direction that I need for the direct comparison. And here's what you're going to do. And it's actually really simple. Look across your numerator. What is the leading term of the numerator's polynomial? Let me make sure you can see that. What is the leading term of the numerator's polynomial? Yep. If I'm heading to infinity, that plus 3n, while holding me back a little bit, as I head to infinity, it has less and less of a grip until when I'm really getting out there, I don't even feel the tug anymore. And essentially, this doesn't affect where this ends up at as I head to infinity. So write down just the leading term. Then, when I look at the denominator, I see a square root and a polynomial under the square root. So put down the square root and then look at the polynomial under that square root. What is the leading term of that polynomial? And by the way, you may see this quicker. What I'm trying to do is give you a generic way to deal with these types of problems. When you look under the square root, do you see that n to the fifth is the leading term of that polynomial? So cut off the excess that's dragging you down and put in who's actually going to lead this denominator to infinity. That's what you want to compare it to. You do need to still simplify. And you're going to simplify quickly or slowly, whichever it may be. It doesn't, just... some of you were seeing that this square root of n to the fifth is n squared times the square root of n. You could use that to your advantage. You could also just throw in exponent rules if you need to. But essentially, you don't have to write all the work I'm writing. You do not have to write all the work I'm writing at all. You just need to figure out what you're going to compare it to. And you don't have to explain your work. I'm just showing you in detail how to get to that answer if it's not obvious to you. So that's how you find out what you should compare it to. So I am going to compare to the infinite series of 2 over n to the 1/2 power. I'm just going to kind of circle this. This is the work that doesn't have to be shown. Now take a look at that. What kind of series do we have? What is our comparer? It is a p series. It's a p series, and the p is equal to 1/2. And what does that mean? It is less than 1, therefore diverge. It is good form to explain what about this test is working to create the conclusion. I have chosen not to accept tests if you either write that it's 1/2 or that it's less than 1. Because it always ended up that people were confused as to how much had to be written, and then people would know, never mind, I'm not going to talk about it. So anyway, know it's good form. You should get into the habit of writing all of it. So you've decided who to compare it to. You've figured out why that series diverges, and you've said what causes it. There's one thing left. And I recommend you use the limit comparison test. But I will say it's possible the direct comparison test will work, but I highly recommend limit. When you use this, you don't have to worry about the inequality being in your favor. And then you're just going to do limit as n approaches infinity of the formula you were given, divided by, whoops, I don't have the whole given. Nope, that's a 5th power. Okay. The formula I'm given divided by the formula I am choosing to compare it to. And as long as I brought this 2 with it, this limit is 1. And because it is positive and finite, that means they both converge or they both diverge. And at that point, you are able to make the final statement of the original formula diverges. The tests that are used, just to emphasize, I started writing tests instead of the tests, our limit comparison test. And actually, I meant to write the word. I started writing different than what was in my head. Stop having a mind of your own, hand. Limit comparison test and p-series. And that's time up on top of it. Woo! Did it. Tomorrow, I'm not going to go into the next test. I'm just going to thoroughly go over homework questions and make sure you're clear of all the tests you have so far before throwing the last one on you. So you are free to go. I need to stop my recording if I can